What do you think? You're going to start with equation condition 1 or condition 2, condition 3, or not this one, right? Come on. Don't make your life miserable. So don't start with this one because anything. Is it 1 or 2?
2.
2. Very good. Why? Because there's no constant. Right? Correct. You start with 2 and you replace one with the other. So you replace either omega z with omega x or vice versa. So what's the step? What's the next step? So this is the first one you choose. Next one is you go back to equation 1. Now you see here, because you have omega y. So that tells you that for step 1, for condition 2, you have to what? Replace omega z in terms of omega x. Right? Because of this one has only omega z, omega y and omega z. So this one is omega z and omega x. So you have to replace omega y in terms of omega x. And from here, you can get this omega z in terms of omega x. Right? So everything will be written as omega x. Correct? Now you have this, and you can come back to here to replace omega y with omega x. So in this case, VB will be written as in terms of omega x. Then we can solve it. So in the end, I will give the values. In the end, omega x is found to be 1.2245 radians per second. Omega y is found to be 1.3265 radians per second, and omega z is found to be 1.8367 radians per second. This is the final answer for omega. Now, of course, in the meantime, we can also find out the value of VB, right? We can all solve it. VB turns out to be 10 feet per second. Now, VB as a vector is what? Is 10 times k. Because it's positive, so it's a positive 10. That means going up in positive direction. And the unit is feet per second. And that's how we solve this problem. Now, if you check this result to see if this result makes sense. Which means what? Which means that if this color A is moving toward the left, the color B will be moving to the up. Because it's positive 10. That means VB here is positive 10 at 10 feet per second. Does it make sense? Yes. Right? It makes sense. But imagine that you have this rod. If you can build a mechanical device like this, what we found when this one moves goes out to here, this one is how it spins like this. But when this thing is moving toward here, and this one, of course, goes up. That's why this result makes sense. Okay, any questions on this example? All right, and I think that I may not have time to finish. Actually, I do have some time. Let's not waste it. Okay. The next topic is about products of inertia. Now I'm going to explain to you what is the relationship between moments of inertia and products of inertia in mathematical form. You already have the definition from me on Wednesday, so I will not repeat that. But here, how do we see them mathematically? In fact, when we defined any subjects, Of course, if you consider a plate, I keep using the plate because it's easier for you to imagine. And the mass moment of inertia of this plate, like the value I use from the back of the textbook, at the center of gravity, with the XYZ defined like this. If this X, this is Y, and this is Z, and the dimension here is B, and this one is A. Of course, the thickness is T. Once again, we always assume that T is much less than A and B. T is much less than A, and T is much less than B. Because if this is not true, and you have to revise this expression. So if that's the case, we know that Ix is 1/12 of mass times the dimension perpendicular to the x-axis, which is what? It's not A, because A is on the x-axis. So it must be perpendicular to it. Now you have two different choices, is either B or T. Since we said T is much less than B, so we can ignore the T, the contribution of T. So this is gonna be 1/12 of M times B squared. For Iy, it's going to be 1/12 of mass times A squared. So B is in the direction perpendicular to X. A is in the direction perpendicular to Y. You can check that. Now what about Z? Z is 1/12 of M times A squared plus B squared. Now, if I said A doesn't equal to B, A is not B. In this case, you can see that if B is greater than A, that means it's more difficult to rotate this object with respect to the x-axis compared to the wand with respect to the y-axis. But the most difficult one is actually this, because mathematically, this magnitude tops Ix and Iy, right? Now, what is products of inertia? Products of inertia is, suppose I want to know the vibrations, the rotation. Who said I have to spin the whole thing, always with respect to this orthogonal, very beautiful axis? Nobody says that, right? In reality, how do you know that? What if you cannot control the rotation of this any object that you consider? What if you can only consider the rotation of this object with respect to not any of these axes? And how is that possible? It's possible if I connect this plate with another bar, and this is a rigid bar like this. And I said I want this rigid bar, and of course rigid bar connects to the 45 degrees, and then I'm going to introduce angular motion to the bar, which means it's going to go like this. And there's also angular acceleration, right? When that happens, can you use Ix, Iy, or Iz? You can't, because the axis of rotation is neither X nor Y nor Z, right? So that is a scenario when you have to use products of inertia, not moments of inertia, because this is not any of this. Now, mathematically, that means what that means. You can actually consider 6 of them. So in general, products and moments of inertia can be written as a matrix like this. So here on the diagonal elements, you have Ix, Iy, and Iz. And these are moments of inertia. The diagonal elements are moments of inertia. And off diagonal elements, which is the 3 here, 3 here, of course, this must be a symmetric matrix. They are products of inertia. So here is going to be Iy, Ixy, Ixz, and Iyz. And this must be symmetric. So we have 3 values for moments of inertia and 3 values of products of inertia. Now, the problem that we can consider here is this. This is, of course, very easy for you to determine what is the XYZ because it's a regular shape. What if we say that we have an object, any object like this? Can you determine what is the XYZ of this one? Now, it may not be that easy, right? So the problem we can convert this back and forth is actually by providing expression of I. Suppose you have a matrix, and if this matrix have non-zero values here, you have this 4, 2, 2, 2. If you don't choose the principal axis, you will always have a full matrix, which is not just with the diagonal elements. So when that happens, that means you choose an arbitrary axis, because for this object, omega s here, suppose you consider an XYZ, and if you use this XYZ, they are not necessary to be the principal axis. In this case, for this three-dimensional plane, the XYZ are what we call principal axis. If you choose any three axes here, X prime, Y prime, and Z prime, they are not necessarily to be the principal axis, unless you're lucky. Correct? So if you do that mathematically, you usually will end up with getting a full matrix. And after the quiz 3, I will show you how we can convert this from whatever you calculated to identifying the principal axis. And that's what we'll do after the quiz number 3.